Hi, welcome back. Today's session is going to be the last part of software design. This is Balu here from SPTech Bangalore. We're going to talk on two things in relevance to design that is called as design notations and types of design notations. First, we shall try and understand what exactly you mean by a design notations. Notations allow design to be described precisely, which means that once you have an architectural design, we need to further define that design more precisely using a notation, and that description can either be using a form of a text or a graphic. Now there are different types of design notations, like you have data flow diagram, structure charts, pseudocode, structured flowcharts, decision table, and PDL, program design language. Now if you remember, there are two paradigms basically for modular decomposition. One is called the function oriented approach, and the second one is called as an object oriented approach. Now the design notations what we are actually seeing here, they are all design notations for function oriented approach, but there are certain design notations for object oriented approach as well, but we are not going to touch those design notations in this particular session. Probably we shall touch on those notations in my next session. Now the first design notation we are going to learn is called as a data flow diagram. Now as the name itself says, data flow diagram, that it's a diagram which basically shows a data flow. It is a DFD will represent how the data will flow in a system when it is built. Though that is the main purpose of a DFD, which will actually show how the data flows from one part of the system to the another part of a system. And you should know that a data flow diagram generally focuses on three important things: inputs, outputs, and central transformations. So what are these inputs, outputs, and central transformations? We shall understand this when we actually look at an example of an data flow diagram. Now in order to write a data flow diagram, there are certain symbols used, and there are two creators who came out with these symbols. D macro and Jordan symbols are one set of symbols. They are called D macro and Jordan symbols because the creator was D macro and Jordan. And there's another set of symbols which were proposed by Gann and Sarson. Now either you can use the Jordan symbols, or you can use Sarson symbols for data flow diagram. So it depends upon your choice. But whether you use either Jordan or Sarson, the DFD symbols has got four important components. The first component is called as a process. The second component is called as a data store. The third component is called as a source, which is also called as a sink. And the last component is called as a data flow. Now all these four components put together will actually make up an data flow diagram. Now we shall see one by one what are these components. First we shall understand what is a source. Now everything begins from a source in a data flow diagram. A source is also called as an entity. Now people could be sources, or business organizations could be sources. They actually form the boundaries of your data flow diagram. If you want me to give an example, let's say that you are building a system for your college. Now the source of that data flow diagram could be your lecturer. He could be a source. A student could be a source, or these sources could also be very conceptual nature. Something like course of a college automation system can also be a source. Now what is a data store? Data store is a place where actually the data is going to be stored. We also call a data store as a repository. A perfect example of a data store could be a simple table of your database management system. You have a process. A process is something which actually converts input to output. It actually does the central transformation. The data from the source actually enters into a process. The process does some processing of data and actually transfers it back to the source, or it actually stores that particular data into the data store. And the data flow is the path in which the data flows. So these are some of the symbols what we use in our data flow diagram. Now there are different levels of data flow diagram. We call them as context level data flow diagram, which is called as level 0. Now initially whenever we write a DFD, we start with an context level DFD, and finally we break down that context level DFD into level 1 DFD and level 2 DFD. As the name itself indicates, level 1 and level 2 are more meaningful representations of the context level DFD. Now this is a solid example of a context level DFD where we have taken an system called student registration system. Know that in a context level DFD I have only represented the entities here, or I have only represented the source or sink. Now student is a source here, college is a source here, and course is a source here. So they mark the boundary of the particular system called student registration system. Now this is a very abstract level of a data flow diagram where people can really understand what are the various entities which are actually involved in this particular system. Now this itself will not give me a clear picture of the data flow diagram in detail. So what I have to do is I have to break down this student registration system into level 1 DFD and level 2 DFD if at all it is needed. So I have only taken level 1 DFD into picture here, where that entire system, student registration system, this process has been broken down into 3 sub processes. Check course available as one process, enroll student as another process, and confirm registration as another process, and have named this process as 1.0, 2.0 and 3.0. And know that each process is calling another process in a sequential order here. And here we have an entity called as a student who is the source of the data. Now there is a data flow here, and I am sending the application details. Now student will generally give application details to this particular process called check course available process. Now what this process will do, it will actually talk to a data store called courses. As I told you earlier, a data store is a repository of data. So there is a table here called as courses, and that course table will actually contain the list of courses available in the college. Now a student would want to seek an admission for a particular course. So what this particular process will do, it will check whether that course is available or not. For example, a student here would want to take up an course called BCA. Now what this process will do, it will check whether that BCA course is available here or not. If the BCA course is available, then this particular process, it will call another process called enroll student. Now what this enroll student process will do, it will actually enroll that particular student, and in the process of enrolling, it would need the course which the student would want to enroll. So the student would want to enroll for a BCA course, so that BCA course details would be taken from the course details, and the course enrollment details will be actually put back into a repository called courses. And once it is done, then it will call another process called confirm registered process. What the confirm registered process will do, it will actually push all the student details to a table called student, and it will give an confirmation back to a student saying that you have successfully registered for a particular course. Now this is how a simple level 1 DFD looks like. If you find that this level 1 DFD is still confusing, what we have to do is we have to break down this level 1 DFD into level 2 DFD, where this process check course available itself can be broken down into number of processes. Now this is the first design notation what we have learned. Now next design notation we are going to learn is called as a structure chart. Now what is a structure chart? They are derived from DFDs. Now DFDs itself may be very confusing sometimes. It may not give us a clear picture of data flow. In order to get more clear picture of data flow, we have to break down the DFDs into structure charts. So as you can see, structure charts, it represents system in more detail than DFD, and it shows the breakdown of a system to its lowest manageable parts, which means structure charts gives more meaning and it puts more light on your data flow diagram. Now a structure chart will have certain symbols, and it also has got certain notations to follow. Now this is a simple example of a structure chart where I have a module, and this module is actually calling 3 modules. module 1, module 2 and module 3. Now since this module is directly interacting with the three modules, so this module is called as a control module and these modules are called as an sub-modules. Now you can do modular decomposition using structure chart in this way, where a sub-module can be called via an control module. There's another way of calling modules via a main module where it goes on a particular condition. For example, you have a main module here. This module either calls module A or module B based upon a particular condition. See, for example, a student is going to register for a particular course. Now, if he is making an online payment, then I am going to call one module, or if he is going to make a check payment, then I am going to call another module. So an online payment will be processed by module A, the check payment will be processed by module B. So this is another notation which we commonly use in a structure chart, and sometimes we also use looping in a structure chart. Now what is a looping in a structure chart? Where module continuously calls module A and module B. That is, the main module continuously calls module A and module B based upon a certain condition. Now one example I can think of is you want to calculate or do a processing of a salary for all the employees. Now processing of salary has got two stages. One is calculation of the salary and the second one is printing of the salary slips. Calculation of salary and printing of the salary slips has to be done for all the employees present in the organization. So in that context, what happens? Now you have list of employees which are there in this particular module. All these list of employees will be taken one by one, and a module A is being called for every employee for calculation of salary, and a module B is called for actually printing of the salary slip. And this module A and module B are called repeatedly from the first employee to the last employee. So we can actually put it in an iterative fashion. So this is another rotation what we use in our structure charts. Now structure charts also has got two types of flows, okay, between modules. We call them as a data flow and a control flow. Now when two modules are interacting with each other, either I pass in data between the two modules or I pass in the control between the two modules. Now on the left hand side you can see it's an example of an data flow. On the right hand side you can see a representation of a control flow. The only difference between a data flow and a control flow is, in a data flow I have an arrow with an small bubble there, but the bubble is not filled with any color. But in case of a control flow, I fill it with a color. So that is the only difference between a data flow and a control flow. But we'll understand what exactly you mean by a data flow and a control flow after we consider an example. Generally a control flow is nothing but a flag, whereas a data flow is nothing but you are sending a data or a data structure from one module to another module. Now have a look at this particular structure chart where there are three modules: open account details, validate account number and display account information. Now open account details module is in turn calling these two modules, validate account number and display account information. Now when you are calling a module called validate account number, this open account details is actually sending a particular data item here. Okay, now this data item is called as an account number, which means if I want to validate the account number, I should first send whether that account number is existing or not. If I want to check whether the account number is existing or not, the data item called account number has to be sent to this particular module called validate account number. If that account number is existing, then this module is going to send an control flag to obtain account details module. The control flag could either be true or it could either be false. If it is true, which means that the account number is existing. If it is false, it means that the account number is not existing. Assuming that that particular account is existing, then what happens? It is actually sending that account number to another module called display account information. Display account information will actually display the details of that particular account. So in this case, we can call this account number as data couples. Now why we call them as data couples? Because they are actually used to couple the data, or they are actually used to call two different modules for actually getting the more information. Now, apart from structured charts, there is another design notation, what we call them as structured flow charts. So in programming, there are three different things which are of importance. One is called a sequence, a selection, and an iteration. Now, a structured flow charts include all of these or any one of these. It depends upon the programming logic. Now, what exactly you mean by a sequence? A sequence means the instructions are executed one after the other in a sequential manner. That is, you have instruction 1, then you have instruction 2, then you have instruction 3 executed in a sequential order. But in case of a selection, the instructions are executed based upon a particular criteria. A simple example of a selection could be if then or an if then else ladder, or even a case statement, and the iteration is nothing but the repetition of statements based upon a certain condition, something like you have a do while loop or a while loop. Now when you put all these three things in a form of a pictorial representation, then it becomes an structured flowchart. Now you can see a simple example of a structured flowchart design notation here. As you can see, there are three things: sequence, selection, and loop, which is an example of an iteration. Here step A is calling step B, which means that B is executed after A, so it is happening through a sequence. And after step B, there is a condition which is going to be checked here, and we are calling it as condition C. Depending upon the outcome of that particular condition, either it is going to step D or step E. Now after going to step D or step E, it is coming to an loop where it is going to check for a condition, and the statements are getting executed as long as the condition is true. So you have a combination of sequence, selection, and iteration all put together in form of a flowchart. So we can call this as a structured flowchart. So this also is a simple solid representation of your design notation. Now apart from structured flowchart, we have another notation called structured English. See, as I told you in the beginning of the session, design notations can be either in graphical format or in the form of text format. Now in the graphical format, you had data flow diagram, you had structured flowcharts, you have structure charts, but in the textual format, you have something called as an structured English. So what do you mean by a structured English? It represents the logic of the code in simple English-like language. See, sometimes it is very easy for you to put the entire logic of a system in English rather than representing it in pictorially. So in that case, we are going to use something called a structured English. Now whenever you write a structured English logic, it is only for the purpose of understanding. It cannot be implemented directly as a code of software. Now even in structured English, it also makes use of sequence, selection, and iteration. And I'll give you a simple example of structured English here. Now just have a look at these snippets of structured English. If client contact is SPTech, set discount rate to 20%, else set discount rate to 10%. So in this case, we are just ensuring that checking for the contact of SPTech. If the client contact is SPTech, then we are setting a discount rate to 20%, else we are setting the discount rate to 10%. Or a simple structured English where do while there are more customers in the list, calculate billing, generate receipts, update database customer underscore master. So what is happening is as long as there are customers in the list, that means for all the customers in the list, I am actually performing three processes, that is calculation of billing, generation of receipts, and after updating of the database customer underscore master. Now all these are examples of your structured English. Now we have another text representation called as a pseudocode. Now a pseudocode is slightly different from structured English. Now what is the basic difference from pseudocode to structured English is it is written more close to programming logic, whereas structured English does not hit on the program at all, but in case of a pseudocode it is more closer to programming logic. Now have a look at this simple pseudocode here. I have got start and end. I have got notations like display, get, and I have used some arithmetic operators here. So pseudocode is also similar to structured English, but it has got slight relevance to programming. Again, even pseudocode is also not executed on computers directly. You cannot just feed this pseudocode to a high level compiler and ask it to compile. It is only written for the purpose of understanding. You have to later on convert this pseudocode back to a programming language and then execute it. Now the one more design notation you are going to learn is called as an decision tree. Now what is a decision tree? Decision tree is basically written if you have multiple actions to consider based upon a certain condition. As you can see here, a decision tree is a graph that uses a branching method to illustrate every possible outcome of a decision. Now I have a condition here. Now based upon the output of this particular condition, I am going to check for two conditions here, which is actually shown here, this condition and this condition. If this condition evaluates to true, I will take this action. If this condition evaluates to false, I will take this action, that is action 2. If the condition evaluates to true, I will take action 3, and if the condition evaluates to false, I will take action 4. Now this type of evaluating the conditions and taking relevant actions is called as a decision tree. But this decision tree can become very complex if the number of conditions are more and number of actions are also more based upon the condition. So instead of writing a very complex decision tree, it is always easier to put it in a form of a table. So we have a new format here coming up, and that format is called as a decision table. Now what is a decision table? It's a type of design notation which will ensure to make decision making and understanding the decision making very easier. And this decision table has got 4 quadrants. Okay, we call them as a condition quadrant, a alternative quadrant, and an action quadrant, and an action entry quadrant. So where do we use a decision table? It is used for decision making purpose, where a table represents condition and respective actions to be implemented in a structured tabular format. And you should know that it is a textual and tabular representation of a decision tree. Now have a look at this decision table which I have shown here. Now there are 4 quadrants here. This is called as an condition stub. Okay, this is called as an action stub, what you can see here, and these are condition entries. Now this decision table is for troubleshooting your printer actually. Okay, now assuming that I want to troubleshoot a printer for its various malfunctioning. Now there are certain conditions here. For example, a printer does not print is one of the condition, a red light is flashing is one of the condition, and printer is unrecognized is one of the conditions. Now the rules have been given here. Now how do I read this? Printer does not print, the condition is satisfied. A red light is flashing, even this condition is satisfied, and printer is unrecognized, this condition is satisfied. So what action I am supposed to take? I am supposed to take the action of check the printer computer cable, ensure printer software is installed, and check or replace the ink. So if these 3 conditions are satisfied, I need to take these 3 actions. Or now come to the second rule, where the printer does not print, a red light is flashing, but the printer is unrecognized, this condition is not satisfied. That means the printer is recognized. So in that case I am going to take these 2 actions, that is check or replace ink, or check for paper jam. So that means for these set of conditions I have certain set of rules. So based upon these set of rules, whether it evaluates to true or false or yes or no, I can actually jot down the set of actions in the action stub. So all the actions are put in the action stub, and all the conditions are put in the condition stub, and all the rules are actually marked in the condition entry. So these are the 4 quadrants what we have in a decision table. So like this you can have any number of conditions and any number of actions, and the representation of that becomes very simple using an decision table. Now in a decision table you have a very important concept called applying default rules. Now have a look at this. You have condition 1, 2, 3 and 4, and there are some rules which have been mentioned here. Now if all these conditions satisfy these rules, okay, for example you have condition 1 satisfied, condition 2 is satisfied to X, condition 3 is satisfied to no, and condition 4 is satisfied to no, then can I take a default action called yes. Similarly, if these rules are satisfied, the default action is X, yes. If these rules are satisfied, the default action is yes, and if these rules are satisfied, the default action is yes. So like this you can have even default rules applied onto a decision table. Okay, now what are program description languages? Now program description languages are for designing slightly higher level than the code itself. It's something very similar to a pseudocode. A pseudocode is a solid example of an program design language or a program description language. Use English like statements that precisely describe specific operations, something like input, where we are accepting the input from the user, or a PDL code contain an output statement, or a PDL code contain an declaration of a variable. So you know, program description language are very again closer to a programming language, but they are not merely programming language, but they are slightly different from an structured English. So write PDL at a low enough level that generating code from it will be nearly automatic. That means what? Your PDL, after you have written the PDL, the next step would be to actually go and convert that PDL into a program code. Now we will see what exactly is an domain specific architecture. Now in order to understand a domain specific architecture, first we shall see what is the meaning of a domain. Now a domain is actually nothing but a field of study. For example, now you have banking domain, your insurance domain, etc. Now there are two types of domain specific architecture models. We call them as a generic model and a reference model basically. Now we shall understand what do you mean by a generic model and what do you mean by an reference model. Okay. Now generic model means they are abstractions of number of real-time systems, and they encapsulate the principal characteristics of these system. Now generic, as the name itself says, it is in more generic fashion. That means it has come after multiple number of experiences which has come here. So in case of a generic model, so here you have a system. A system will consist of an input, a process and an output, and this input is actually talking to the database and the output is also talking to a database. And the type of an generic model we are going to discuss here is called as an data processing model. Now whether you take a banking system or an insurance system or any other kind of system, you need to have a data processing model. So you cannot have a banking system without a data processing model, because a banking system would actually need an input and an output. Even an insurance system also would need an input as well as an output. So when you are building an system, you would need certain generic models. So these generic models are the models which are available and which can be reused. For example, data processing model is defined like this. Either you can use the same model or you can slightly make some modifications to this model. That is why we have mentioned here data processing model can be reused. So they are abstractions of number of real-time systems, and they encapsulate the principal characteristics of the system. That means whenever you think of a data processing model, you should think of a system with input, process and an output, so you can make use of this particular model for your application. Now there are other type of models called as reference model. They are more refined than generic models, hence contain more information. Generally, generic modules do not contain all the information. We need to go for another type of module where there are more information present there, and that is actually called as a reference model. They may incorporate all the features of a system. So generally, reference model incorporates more features than a generic model, and it can act as a base against which system can be evaluated. So let's look at an example of an reference model, and one such example of an reference model is called as an OSI model. OSI model stands for Open System for Interconnection. As you have studied this in your networking subject, the model consists of 7 layers, that is physical layer, data link layer, network layer to application layer. If two systems has to interact with each other, they have to interact on this particular 7 layers of network. Now these 7 layers of network becomes an reference model for communication. So domain specific architecture talks about generic models and reference models. That's it. Thank you for watching this particular video lecture. Do subscribe to our channel SPTech, and don't forget us to like us on our Facebook page SPTech BANG. I will see you on my next video lecture. Till then, take care and bye bye.